In this video, we're going to be looking at topic 1D, the periodic table, and we're going to be focusing on the outcomes that are both in the single and the double science course from Edexcel for IGCSE chemistry. So we'll be looking at how we arrange elements in the periodic table. We'll also touch on the electronic configurations of the first 20 elements, how we classify and identify elements as metals and non-metals based on some of their properties as well as their position in the periodic table. We're going to link the electronic configurations to the position of the periodic table and also then why we have similar chemical properties with some elements, and then focus on the noble gases and look at why they do not readily react with anything. So the periodic table you'll have met before back in Key Stage 3, most likely in Year 8, and it consists of a series of columns, which we call groups, and rows, which are called periods. Now, some of the groups have names, and you will be expected to know these names, and the elements making up these groups have specific chemical properties, and they share a chemical property. Most of them will react in very similar ways. It will just be different levels of reaction. Now, we can split the periodic table into various different categories. We can look at metals and non-metals, we can have solids, liquids, gases, and natural versus synthetic. So we're going to look at some of these. So this is what the periodic table looks like when we remove the elements and we just keep the general shape. So you can see that we've got some specific groups. So we have group number 1, which is known as the alkali metals, and this is from lithium with sodium and potassium and so on. We then have group number 2, which are known as the earth alkali metals, or sometimes the alkaline earth metals. Groups 3, 4, 5, and 6 is this purple box here, and we don't give them specific names. They have similar chemical properties, and they are obviously still groups of the periodic table, but we don't put that much focus on them. We then move to group number 7, which is known as the halogens. That's your fluorine, chlorine, bromine, iodine, and astatine. And then group number 8 is the noble gases, sometimes known as group 0. And the noble gases will be helium, neon, argon, and so on. This part in the centre is known as the transition metals, and we don't give these group numbers. So your group numbers jump from number 2 here to number 3 here. So we ignore this section in the middle. These are our transition metals, and you'll learn more about the transition metals at A level if you go on to study A level chemistry. Then down the bottom, we have 2 sections which have sort of been pulled out of the periodic table, and you'll see that in the numbering, and we call these the lanthanides and the actinides. Now, we very rarely speak about these. You may discuss them in physics when you're talking about radioactivity. You may look at the lanthanides and the actinides in terms of their elements, but we don't talk about the actual reactions of these particular elements. Our main focus is going to be groups 1, 2, 7 and 8. They'll be the ones that we'll talk about in terms of patterns and looking at their chemical properties. Now, we can also split the periodic table down just simply into metals and non-metals, and we have a zigzag line you'll see here that looks like a staircase, starting at boron and going down in a staircase fashion down to astatine. Now, everything on the right hand side is your non-metal, so this small section on the right is our non-metals. So you can see the majority of the periodic table is actually your metals, and that's the part on the left hand side of the zigzag. So this is important when we're discussing the specific properties. Metals will have certain properties that non-metals won't, and vice versa. We can also look at solids, liquids, and gases in terms of the periodic table, and the majority of our periodic table are going to be solids. This is important when we're looking at state symbols and chemical reactions. We have 2 that are liquids at room temperature. So these are all the states of matter at room temperature, and we're talking about 25 degrees Celsius as room temperature. And the 2 liquids are mercury and bromine. 1 metal, 1 non-metal. It is extremely important that you do remember those. They do sometimes come up in chemical equations, particularly bromine, and they will be looking for you to have the correct state symbol. So remember, of course, your state symbol would just be L in brackets, S in brackets for solids, and for gases, it would be G in brackets. And our yellow ones here are our gases. So all of group 8, because these are of course called our noble gases, are going to fall into the gaseous state. And then we have nitrogen, oxygen, fluorine, chlorine, and hydrogen. So majority being our solids. We could also look at them of what is naturally occurring and what is man-made. Now this doesn't really come up that often in exams, but it is useful for you to know that all of the elements except number 43, which is technetium, between numbers 1 and 98, and remember this is their atomic number, which we discussed previously is the number of protons in their nucleus. So between 1 and 98 are all naturally occurring. From 99 up to 118, these have all been made in the lab. So these are synthetic or man-made elements. And as we said, that one exception being number 43, technetium. So it's important that you know how to classify different elements in the periodic table. And we're going to look a little bit later on at how we tell the difference between a metal and a non-metal. But most of it is common sense, and you will have seen this before. One thing that we're going to focus on that you probably haven't seen before is the electronic configuration. So we've previously discussed electrons, and we know that these are a negatively charged particle that we find in an atom. In an atom, they are going to be the same number of protons as for electrons because they have to be balanced out, and they are found orbiting the nucleus. So they're very, very small particles that orbit around the nucleus. Now, what's important to note is that they are not just randomly orbiting the nucleus, going in whatever direction and any position that they want. They are actually arranged in something known as shells around the nucleus. Sometimes you may see this as orbitals, or you may see energy levels. For now, these three words are going to mean the same thing. Once you get to A level, you may find that there are some slight differences, but we're going to use either shells or energy levels. They'll be our two most common words, and they're all arranged around the nucleus. And each of these shells can hold a maximum number of electrons. So our nucleus in this diagram is our black dot here. The first shell is just a circle around the nucleus, and it's quite small, so it can hold a maximum of 2 electrons. We move to the second shell, which you can see is just, again, we're just going to continue to display them as circles. And our second shell is a little bit bigger. It can hold a maximum of 8 electrons. And the third shell, again, that circular square, just a little bit larger, it can also hold a maximum of 8 electrons. Now, you will only be required to discuss the electronic configurations for the first 20 elements. After the first 20, it becomes too complicated for GCSE. That's something that you'll discuss at A level, where you'll look up to the first 36. But we're just going to keep it nice and simple at GCSE and focus on the first 20. So from hydrogen through to calcium. Now, there are a couple of rules about when you're filling electrons into a nucleus, and you will be expected to be able to draw out electronic configurations, but it is much easier than what you think. So the first rule is that our lower energy shells have to be filled before the higher ones. So we start by filling the first shell. Once that's full, then we move to the second shell, and we only move to the third shell once the second one is full. So you don't put electrons into shell number 3 or 4 without filling 1 or 2 first. So the lowest energy level is the one that's closest to the nucleus. So if we've got our nucleus, we have our first energy level like that, and then our second energy level. Now our first energy level, or our first shell, can hold 2 electrons. So we draw it like that. And we draw the electrons as crosses, or you can draw them as dots. And you'll learn more about how we use this to show bonding when we look at covalent bonding. So we're just going to say for now, our electrons are being displayed as crosses. Now, for the first shell, it's quite simple because there only are 2 electrons that can fit. So when you get to the second shell, it is a little bit different. We can fit a maximum of 8 electrons. So our second shell holds 8 electrons, and that E with the shortened symbol with the minus sign is just a shorthand for electron. Now these electrons, again, they don't just go in randomly. They should be paired together. But electrons will not pair up unless they have to. So what you need to think of is you need to think of 4 positions in this shell. And it's like a clock. You've got a position at 12 o'clock, 3 o'clock, 6 o'clock, and 9 o'clock. Top, bottom, side, side. Those are the position of the electrons. And when the electrons are being added, they will always go as far apart as possible. So they will not pair unless they have to. So you'll do top, bottom, and then left and right will fill. Now, once I'm putting my 5th electron in, I have to start pairing because I now no longer have any extra spaces. So I will pair the top, I would pair the bottom, and then pair the right, and lastly the left. So you will end up with a diagram that looks like that. And that tells us that in our first shell, you have 2 electrons, and in our second shell, you have 8 electrons. And that's how we write out the electronic configuration. So we can figure out what element this is by determining the total number of electrons, which is 10, and then that is our atomic number. So this is the electronic configuration of neon. So you may be asked to determine what the element is from the electronic configuration, or you may be asked to draw it. So let's look at an example of how we draw out an electronic configuration. So we're going to pick oxygen. Now oxygen has an atomic number of 8. And we want to draw out its electronic configuration. So we're going to have our nucleus in the centre, and you can put the symbol, so our symbol in this case is O. We're going to have our first shell, and we know that we can fit 2 electrons in that. So I'm going to write a 2 to tell me my first shell is full, and then a comma. Then I need to start filling my second shell. And remember, we're going to fill it in like a clock face. So we're going to do top, bottom. So there's 4 electrons in total. I've got 4 more left to add. I'm going to do right and left. So now I have a total of 6 electrons. I have 2 more to add into my second shell. I have no more free spaces on their own. So now they have to start pairing. And I'm going to pair top and bottom like that. Now I have 8 electrons in total with 6 in the second shell. So my electronic configuration for oxygen is 2, 6. If we look at aluminium as our next example, aluminium has an atomic number of 13. So we're going to draw our nucleus, and we have Al as our symbol. We're going to draw our first shell, and that's going to be filled with 2 electrons. We're going to draw our second shell. Now we know our second shell can hold a maximum of 8. If we add those 8 electrons to the 2 we already have, that gives us 10. We need at least 13. So we know our second shell is going to be full. So I'm going to put in my electrons singly, then pairing them. And I have 8 in my second shell. I now have to move to my third shell. And I have 3 electrons left to place. So I have 1 at the top, 1 at the bottom, and then it can go on either side. It does not matter. And I have got 3 in my outer shell. So my electronic configuration for aluminium is 283. And the last one that we'll do as an example is carbon. Carbon has an atomic number of 6. So I have my nucleus with the letter C for carbon. My first shell is going to be filled because, of course, as we've said multiple times now, that can only hold 2 electrons. I then have to go to my second shell. I've got 4 electrons left to place, so I have my 4 electrons all singly in each of the positions, no pairing, to give me an electronic configuration of 2, 4. Now you may wish to practice this, and your teacher may ask you to draw out the electronic configurations for the first 20 elements. I would strongly suggest that you do practice and you get used to and confident in drawing these, because they do come up in exams and in past paper questions, which we'll see later on. So this diagram shows us the electronic configuration for the first 20 elements. So you can see that we've got the first period, or the first row, so this being period 1, has got only the first electron shell filled. Then we move to period 2, and we're filling the second electronic shell. So we've got 2 numbers in our electronic configuration, 2 electron shells being filled in period 2. Moving to period 3, I have 3 numbers because I'm filling 3 electron shells. And then for period 4, I'm filling 4 electron shells. So actually the number of numbers in your electronic configuration will tell you which period or which row an element is. You should be able to determine the period and the group from the number of outer electrons. Now, elements that are in the same group are going to be able to show the same number of outer electrons. So if we go back to our diagram, we can see that everything that is in group 1, if we look at that last number, which is our outer shell, 1, 1, 1, 1. They all have 1 electron in the most outer electron shell. Group 2 all have 2 electrons, group 3 have 3 electrons, and so on and so on. The only exception is helium, is in group 8. So all of the rest of the noble gases have 8 electrons in its outer shell. Helium only has 2 because it only fills that first shell. So that's the one exception. Everything else, whatever the group number is, tells you the number of outer electrons. So if you have, for example, an electronic configuration of 2, 7, there are 2 numbers, therefore it must be in period 2. So you go to period 2, it has 7 as its last number, so it is in group 7. We go to period 2 and group 7, and that tells us 2, 7 should be fluorine. So you can identify the position of an element in the periodic table by using its electronic configuration to tell you not only the group number but also the period. Now, because they have the same number of outer electrons, they have very similar chemical properties, and you will have actually discovered and looked at some of these back in Key Stage 3. So the first one, alkali metals, group number 1. They all have 1 outer electron. They all react violently with water, oxygen and acid, and the reactivity increases as you go down the group. Now, you don't need to be able to explain why that's the case. You simply need to be able to explain that that trend exists and that they all react with water, oxygen and acid in the same way because they have that 1 outer electron for group 1. And some examples are lithium, sodium and potassium. Group number 2, the earth alkali metals, all have 2 outer electrons. They are again going to react very similar with water, oxygen and acid. So they're going to have the same sort of reactions because they all have 2 outer electrons. And examples are beryllium, magnesium and calcium. Jumping over to the other side of the periodic table, group number 7 is known as the halogens, and they have 7 outer electrons. And you'll look a little bit more at the halogens in topic 2b. When you have 7 outer electrons, again, they're all going to have the same sort of reactions, and this time the reactivity decreases as you go down the group. And some examples are fluorine, chlorine and bromine. And lastly, group number 8 have 8 outer electrons. This is our noble gases. These do not react at all because they have a full outer shell. That means that every electron is paired. So there are no unpaired electrons in the noble gases. And in order for an atom to react, it must have unpaired electrons. So because every electron is paired, the noble gases do not react. And some examples we've met are helium, neon, and argon. So it's important that you do know those rough reactions for each of those groups that we've discussed, and you'll look at the halogens and the alkali metals in a little bit more detail when you do Unit 2. Now we can also look at the properties of the metals in our periodic table versus the properties of non-metals. And again, this is mostly things that you will have covered in Key Stage 3. So you've looked at metals and non-metals in Year 7 and Year 8. So a lot of this should just be revision for you. So metals are going to conduct electricity and going to conduct heat. They are going to form basic oxides, meaning they have a pH above 7. They tend to be solids with particularly high melting and boiling points, the one exception being mercury. Remember, mercury is a liquid at room temp. Metals tend to be shiny when they are polished. They are malleable, meaning they can be shaped. They are ductile, meaning they can be drawn into wires. And they're going to form positive ions when they're in ionic compounds. And we'll discuss a little bit more about ionic compounds in topic 1E when we look at ionic bonding. So don't worry too much about that just now. Now, if we compare that to the properties of non-metals, the majority of non-metals are not going to conduct electricity. There is one exception, which is graphite, which is a form of carbon. And again, you'll learn more about why that conducts electricity when you look at covalent bonding, which is topic 1F. You will look at the fact that non-metals also form acidic oxides, which give you a pH below 7. They tend to have low melting and boiling points, with the exception of carbon and silicon. They tend to be quite dull, they're quite brittle, and this time they're going to form negative ions in ionic compounds. And again, this will be discussed further when you look at ionic bonding. So we're going to finish off this topic looking at some past paper questions. Now remember, when you do any past paper or any exam for chemistry, you will have access to a periodic table. You are not expected to memorise it, but you are expected to be able to navigate it. So familiarise yourself with the periodic table, get used to using it in class and in your everyday revision when you're answering any questions, and the more you start to use it, the more you will start to remember where things are and you get a better understanding. And of course, if there's things that you're not sure about, then certainly ask your teacher. So first of all, the symbol for silver, well, when we look it up on the periodic table, we find that the symbol is Ag. So our answer is A. An element with the atomic number of 40, when you find your periodic table, you go to 40, and that is Zr, which is zirconium. The table below lists some properties of the gases in group 0 of the periodic table. We want to complete the table. So first of all, we want to give the symbol for neon. Now, the symbol we just get from the periodic table is Ne. Now, for the boiling point, you will learn more about this in topic 2B, but you can see the general trend here. The boiling point is going from 4 to 27, then there's a gap, 121, 165. We can see that that's getting higher. So as long as we have something in between these numbers, any number is acceptable. So we're going to put 70 as our answer, because it seems to fit in with the general trend. It's between 27 and 121, and we're trying to go sort of in the middle of those two. And then for the reaction of xenon with metals, well, we can see that none of the others react. We know this is group 8. We know it's a noble gas. So of course, we're going to have no reaction because they have that full outer shell, no unpaired electrons, so we get no reaction. Now, an atom of an element has the electronic configuration 2, 8, 3. We want to look at the number of the group of the periodic table in which this element is found. Well, then we go to our final number. Our number is 3, so this is found in group 3. Easy as that. We want to explain that in terms of the atom's electronic configuration. Well, it has 3 electrons in the outer shell. That's how we know it's in group number 3. Then we want to state the period. So now we look at how many numbers there are. Well, there's 1, 2, 3. So this is going to be in period 3. Again, explain your answer in terms of the electronic configuration. Well, the atom has electrons in 3 shells. The fact that it has 3 shells filled means it must be in period 3. And then lastly, we want to identify the element. We would use your periodic table. We could look and see that that gives us a total of 13 electrons. So atomic number must be 13, which is aluminium. And then the last question, complete the diagram to show the electronic configuration of an atom of fluorine using X to represent an electron. So fluorine, we would look up in the periodic table and we can see that that has an atomic number of 9, meaning it must have 9 electrons. So we're going to start to fill in our electrons here. So our first shell, we know, holds 2 electrons. If I put in 2, I can then need 7 left to fill. They must go in the second shell. The second shell can hold a maximum of 8, so we know they're all going to fit. So we'll have top, bottom, right, left. There's 4. I have 3 more. I'm going to pair top and bottom and at the right here. So I have an electronic configuration of 2, 7. And there's the answers to these past paper questions if you've been trying them alongside me. That's everything for topic 1D, and we've covered all of the outcomes for the single and double content. If you have any questions, please feel free to leave a comment below, and we hope to see you back on the channel soon.